and thank you very much for attending this session. This session is about SETI. SETI is an acronym for Search for Extraterrestrial Intelligence. Well, I guess that many people know already about that, but let me just perhaps summarize very, very quickly what we are doing worldwide, actually. Well, first of all, we use the largest radio telescopes, that is the largest antennas available on Earth, in order to find out whether we can pick up or not any sign betraying the existence of someone else from wherever in the universe. Usually we expect to find someone perhaps in the galaxy, in this galaxy, the Milky Way, because of course the distances are shorter, but we cannot rule out that someone else might like to connect or send signs of life from outside this galaxy. So this is SETI. And I have been doing SETI for many years of my life. Unfortunately, I am 75 now. And I was chair of the IAA, the International Academy of Astronautics, permanent SETI committee for 9 years. Now someone else is replacing me, but the search is continue. And I have to say that the most efficient group, I would say, in doing SETI worldwide is the University of California at Berkeley group led by Andrew Simeon, with the fundings coming from other institutions, especially the breakthrough initiatives. Okay, so this is just to start with SETI. But of course, this is a conference about big history, and I would like to say something about my personal view. It may, of course, not be correct, about the relationship between big history and SETI. Well, let me tell you that unfortunately, my presentation may be a little bit unusual because I am basically a mathematical physicist, and I did my PhD in mathematics many years ago. So essentially, what I would like to tell you in this presentation is that I have published a book, and I am asking Heath, please, to go to the next slide. Good. This is the abstract. EVO-SETI stands for Evolution and SETI. Evolution in the largest possible meaning, of course, evolution of life on Earth. As we know from big history, this may have started 3.8 billion years ago. And SETI, I told you already what it is. It is the current attempts by scientists and radio telescopes to find out signs of alien life. Now, what I did is to publish recently a book called EVO-SETI. So EVO-SETI is the title of the book. And what is that about? Well, that is a mathematical theory that honestly I have been discovering and putting together piece by piece in the 10 years between 2010 and 2020. So it was published little by little in prestigious journals like the International Journal of Astrobiology, Life, OLEB. OLEB is an acronym for Origin of Life and Evolutionary Biosystems, and Acta Astronautica, because of course we use the radio telescope, and we even plan to use in the future the moon far side as an excellent place to do SETI. So this is just to introduce the word EVO-SETI. Now, unfortunately, I have to tell you these quotes, bad news, sorry. EVO-SETI theory, that is my mathematical theory, is difficult mathematics. You must know the calculus, probability, statistics, and astrobiology. However, in this presentation, I will try to keep away from that as much as possible, or at least to explain with simple words what the equation means. So in 2021, the book EVO-SETI, Life Evolution Statistics on Earth and Exoplanet. Of course, the last sentence is the subtitle, Life Evolution Statistics. So I'm talking mathematics, of course, on Earth and exoplanets. Is summarized all this book in this link that you can find, and I have sent my presentation to all the people I knew were going to attend this meeting. So if you find it, fine. If you don't find it, you can send an email to me, and I will forward it to you. And there is also a video, and the video is at the last green side. And essentially, this is a popular explanation that I gave in 2019 when I organized my first International Big History Association conference in Milan, Italy. Okay, next please, Heath. Good, so this is the book. You see the cover, the title, the subtitle, Life, Evolution, and Statistics on Earth, on a Planet, and the picture. Well, what is the picture? Well, the picture is basically a round thing, which is the Earth, or anyway, a planet, an exoplanet, where we hope life to exist. We don't know, because we didn't find anything like that so far, but we are trying to find it. And the background below the big round thing is a part of the Andromeda galaxy, meaning that we use any galaxy, of course the Milky Way first, but also other galaxies, possibly Andromeda, in our SETI searches. Now, unfortunately, I have to give you this bad news. The book is expensive. In euros, it is over 100 euros, and the paperback is 135. This is not my fault, I have to say, because as you probably know, the prices of books are set up by the publishers. And in my case, the publisher is one of the best publishers worldwide, the Springer publisher in Germany. And I'm grateful to them because they did all suggestions of mine to make the book appealing, including colored equations. So it's not just a black and white book, but we have tried to put the equations in colors to help the understanding of the whole thing. Thank you. Next, please, Heath. Now, this is a summary of what my presentation is tonight or today. Well, first of all, I have to say that all this regards past and current life on Earth, only on Earth. Why? Because we only have one example of a planet where life has developed fully in the last, say, 3.5, 3.8 billion years. And so it is important to start from this point. Perhaps in the future we'll do better. I don't know. Anyway, there are 7 parts in this presentation. The first part is about life. Now, let me speak frankly to you, please. I have been attending several conferences about astrobiology and also about big histories. And, what I was surprised and not pleased to hear is that there isn't, of course, a single definition for answering the question, what is life? And this is not good, in my opinion, because science, and of course I am a scientist, I'm a mathematical physicist, needs one definition only that is accepted by everybody. And so in my book and in my presentation tonight is life is a B log normal. I will explain in a moment what is that. Essentially, it is a probability density, probability distribution, but in particular probability density in the time and not in anything else. In the time, meaning that the independent variable of this thing is the time since 3.8 or what, 3.8, 3.5 billion years ago up to now. And I have adopted the convention that all the past times in history, and in big history, of course, are denoted by negative numbers. So you will see a minus sign in front of the times, whereas 0 time is nowadays, that is the age when we are living, and future times are positive times. We don't know about that yet because we didn't find any extraterrestrial civilization, but hopefully we will. And so future discoveries will be denoted with the plus sign in front of the time. Now, part 2, Darwinian exponential growth. Now, this is an old story, of course, and I'm sure that the vast majority of you, of course, has his/her opinion about that. Essentially, I think I've noticed that the pace of evolution is increasing, meaning that when evolution of life on Earth started, for me, it is conventionally set up at 3.5 billion years ago, but it could be 3.8 or 3. Or 4, even 4. That doesn't change anything. It just changes the numbers, but not the equations. So anyway, I could notice that there is an exponential increase in the speed of evolution. So I would like to stress the word exponential, because this is precisely what I've been trying to use mathematically speaking, an exponential in the time, and I will say more about that. Okay, now, one more point, part 3, geometric Brownian motion. Oh my God, this is a technical term used by physicists, and I regard myself also as a mathematical physicist, to describe one particular stochastic process. What the hell is a stochastic process? A stochastic process is a random function of the time, meaning that if you give me a time in the past, I don't know what the value of that function was at the time, but that is not complete ignorance. I know something else. I know the mean value of the whole stochastic process over the whole 3.5 billion years. And I give you also 2 more curves, the curve above the mean value, and this is the upper standard deviation curve, and the curve below the mean value, and it is the standard deviation lower curve. And so essentially speaking, we don't know exactly what is the unfolding of the geometric Brownian motion, that is, of this stochastic process, but we hope or presume that this unfolding is included in between these 3 curves that I mentioned. And the geometric Brownian motion does exactly that. So it has a mean value, an exponential mean value. And I have to say that actually I'm not the first guy who used that at all. It was used by financial mathematicians. People familiar with financial mathematics may have heard about the Black-Scholes models. Incidentally, Black unfortunately passed away before getting the Nobel Prize, but Scholes and Merton got the Nobel Prize in economics in 1997. So they used precisely this thing, the geometric Brownian motion, to describe their equation. So you may say that I have been stealing their work and translated that for the advantage of big history and the evolution of life on Earth and on exoplanets. Anyway, this is the situation. Now, part 4, Darwinian growth is a GBM. GBM, of course, stands for geometric Brownian motion. Darwinian growth is a GBM, and I will say more about that later on. So essentially, I am pointing out this stochastic process as the best stochastic process to describe the evolution of life on Earth and possibly on exoplanet. Now, part 5, entropy is an evolution measure. Now, you will notice in this presentation that I will use different civilization. Of course, we know about the civilization that developed on Earth, but in SETI, we are assuming that civilization develops on other planets, on exoplanets. So we need a mathematical measure in order to find out a number associated with the degree of evolution of that particular civilization. And what I am suggesting is entropy. But the word entropy is unfortunately overused. Of course, it is used in classical physics, in the theory of gases, and I'm thinking about the famous mathematical physicist of the 19th century, Boltzmann and other. But that is not the entropy I'm using. What I am using is the Shannon entropy, put forward by the American mathematician and engineers Claude Shannon in 1948. And I will tell you more about that when we reach this point. Part 6, an example at long last. Well, I felt I had to put in front of your attention one typical clash that occurred on Earth in the past between two different level civilization. And of course, there is, in my opinion, nothing better than the clash between the Spaniards and the Aztecs that took place in 1519. So when we reach that point, I will tell you more. And essentially, I could measure the entropy difference as an information difference between the Aztecs and the Spanish. And essentially, of course, is that the Spanish were much more knowledgeable than the Aztecs. And that's why they won the game, essentially. Incidentally, this is what I am afraid about, because if we find an extraterrestrial civilization, it might be much more advanced than we are. But anyway, we have to prepare for that. And this is what I've been trying to do. Finally, unit of the scale. What scale? Well, the scale of life in the universe that I will be talking about in part 7. And I had to give a unit. You know, in physics, we always have units. My unit is, of course, in information unit, so you shouldn't be surprised to find a bit here. And it is 25.575 bits, called EE, standing for Earth evolution. And this is the number that comes out from my calculations, referring to the evolution of life on Earth since 3.5 billion years ago up to now. Next, please. Good. Bilog normals. What the hell are these? Well, Bilog normals are the curve that I am assuming as describing at best life in the time. So I'm not talking about chemistry. I'm not talking about paleo, whatever. I am just talking about evolution in time. And in my opinion, this applies to cells, animals, humans, civilization, and even ET civilizations. Next, please. Okay, now, just look at this diagram, please. On the horizontal axis, can you see the cursors, please? I hope so. So on the horizontal axis, you have the time. We have the time. The time starts at 0. The time of a living something could be a cell, an animal, a human, a civilization, just something living. Okay, we'll later explain what more that more in detail. So there is, of course, a birth time. Every one of us was born at a certain time, and this is denoted as the point of coordinate small b, lowercase letter b, and 0. So lowercase b is the time of birth here, the beginning of the curve, and 0 is the value on the vertical axis. You ask me, what the hell is on the vertical axis? Well, it is a Bilog normal, that I'm going to describe in a moment, probability density that I will describe later. Now, after being born, every one of us had an initial phase, which is the increasing phase shown here, in between the birth moment and I call that adolescence, just to give it a name. But actually, mathematically speaking, is the point where the second derivative of the curve equals 0. So it is the inflection point. And more properly, it could be called the puberty time. So this part of the curve in between birth and puberty is what astrobiologists and biologists called well, there is a name for that. Sorry, it doesn't come to my mind at the moment, but later it will come up. And then, of course, after the puberty, life continues and reaches a peak, denoted by small p and capital P. and then starts declining. And so it declines until it reaches the point where again the second derivative equals 0. And I call that senility, coordinates small s and capital S. And after that, the real curve, the B-log normal, would go to infinity, is meaning there would be here a long tail reaching the time axis at infinity. But of course, this is incorrect because no living creature lives for an infinite amount of time, at least now. So in conclusion, here I had to change the definition and to replace the curve, the B-log normal, with a straight line going from the senility point to the death point. And of course, I gave names to the various parts. So in between here is childhood, here is youth, this is maturity, this is decline, and the whole thing in between birth and death is lifetime. In between birth and senility is vitality, and in between adolescence and senility is fertility. Next, please. Okay, now this equation here is the equation of the B-log norm. Don't be scared. It looks like a Gaussian, but it is not so. Actually, essentially, in loose terms, if you have a Gaussian distribution, or that is normal distribution, then the distribution of another random variable, that is E, the number E, 2.7 whatever, raised to the Gaussian, is precisely what mathematicians and physicists call the log normal, okay? And this is the equation of the log normal in the time. So you have the time here and the time here under the log, starting from the initial time B, which is the birth time, okay? So this curve applies only in between, with the time ranging in between birth and senility, nothing else. Okay, next please. Once again, this is the same curve. I will save you with this equation, but just from the very definition, you can give a number of equations, which is what I like because I'm a mathematician or a mathematical physicist anyway, and I want to talk mathematics, not words. Please forgive me, but I regard mathematics as much more precise than just words. So anyway, this is just to show you the same curve again, and some equation that come out immediately from the definition. Next, please. Now, here comes something interesting, I guess, for the big history association. History formulae. The name is mine. I had to give it a name because, honestly, I never found anywhere else these equations. And what are these? Well, these are just two equations that give you the two parameters in the B-log normal, that is sigma and mu, expressed in terms that is a function of the point that I described earlier. D stands for death, S for senility, death again, birth, senility, and birth. So this is sigma, the parameter that is called like that because essentially it comes from the normal distribution sigma, which in the normal equation, not in the log normal equation, is related to the variance and the standard deviation of the bell-shaped curve around the mean value. And mu, of course, it comes again from the normal distribution, historically speaking. It is a log of this difference, senility minus birth, plus this term, okay? So these are rigorously proven. And I have to say, frankly speaking, that it is not that difficult. It took me a while to find them because I never saw them anywhere else. But they are not that difficult. Essentially, you are solving a system of two simultaneous equations. And you can solve it first with respect to sigma and then with respect to mu. Now, I would like to give you some practical times, at least for one example. I hope you'll forgive me. As you hear from my accent, I am from Italy. And when I was a child, of course, I was taught history courses about the history of Rome, ancient Rome. that was compulsory in my country, exactly as in the UK, it is compulsory to learn about kings and queens of England, or in America, the same story about the president of the United States. So I had to learn about the emperors and whoever of the ancient Rome. And the point is that the starting of ancient Rome history is the year minus, because it's in the past, 753 BC, before Christ. The adolescence is 146 in the past, that is BC. The peak happens to be at 59, that is at the time of Nero, or Claudius of Nero, emperor, AD, of course. And as, in my opinion, happens at the year 235, when the Rome ceased to be the capital of the empire. So anyway, these are the history formulae. I will give you an example practically in a moment. Next, please. Good. So here is the diagram that you wanted to see. On the horizontal time, on the horizontal axis, you have the time, of course. The history of Rome starts at minus 753 before Christ, of course. It keeps going until about 350, practically horizontally. It is not really horizontally, but practically. And these are the 7 kings of Rome, when Rome was not a republic yet. It was a monarchy, 7 kings. But then around this time, the last king was they got rid of him. And then the curve starts increasing, because this is the Republican time of Republican Rome, and goes up until it reaches the peak. But the peak is already beyond zero. The zero, of course, is the time when Jesus Christ was born, that we used as zero for all days in current history. And so the peak is at, as I mentioned, at the time of Nero, 59 AD, and then it goes down. But these red curves is the full bilog normal. That is, it touches the time axis at infinity. Next, please. Now, this is incorrect, because nobody lives for, or nor any civilization lives for an infinite amount of time. So the point is that the real thing is the tangent line, at this senility point, which is the decreasing inflection point, and this touches the axis at 476, which is assumed by historians as the year when the Western Roman Empire collapsed finally. Okay, next, please. Now, you have understood the trick with the Roman civilization that I know best. But after discovering that, of course, I took a delight in repeating the game with other civilizations. So in the next picture, you will see several more civilizations: ancient Greece, and then ancient Rome, as I mentioned, Renaissance Italy, Portuguese Empire, colonial empire, Spanish colonial empire, French colonial empire, British colonial empire, and USA. I wouldn't say colonial empire, but it's nearly the same, cultural empire, if you like to call it like that. And these are the dates. Don't read all that, but essentially, if you pick up an history book, more or less the dates are more or less correct. Next, please. And here you get the same thing, but in diagrams. So once again, you have the horizontal time axis. 0 is the time when Christ was born. The first curve, the red curve, refers to the ancient Greek civilization, roughly between 600 before Christ and 30 before Christ. 30 is the time when Cleopatra committed suicide, and Egypt was the last Hellenistic kingdom, became a Roman province, of course. Then Rome, as I mentioned already. Please notice carefully that the curve of Rome, the bilog normal, is slightly less high than the curve of the Greeks. Now, this is not by chance, because the Romans, in my opinion at least, were less advanced, culturally speaking, than the Greeks. So this difference in between them, in my opinion, refers to the fact. But then let's go ahead. We have 10 centuries. Oh my God. 10 centuries of nothing. Why? Well, because I'm a pupil of Carl Sagan. I also had the immense privilege of meeting with Carl Sagan many years ago, of course. And the main teaching I got from him was that these 10 centuries were an entirely millennium lost for the progress of civilization on Earth, at least in Europe. And this was simply because that were the so-called Dark Ages or Middle Ages, and everybody was fighting against the next door. And so there could hardly be any progress in civilization in this period. And that lasted until, in my opinion, 1250, when the last medieval emperor, Frederick II, who was emperor of Germany and Italy at the same time, died. And, you know, something new at last happened. And that was the beginning of Renaissance Italy, the green curve. And Renaissance Italy grew up until about the Renaissance time, 1527. This is the time when the Landsknecht in German, the warrior came to Rome and you know, sacked Rome 1,000 years after the first sack, or something like that. And then the curve declines, and finally, after the death of Galileo Galilei, Italy lost the cultural privilege of being the center of the world in some sense. But then here you have other curves, of course. The brown one, which is Portugal, the orange one, which is Spain, this one, the blue one, which is France. I'm sorry, no, this one is the French, the light blue one. The heavy blue one is Britain, the British Empire. And for the joy, sorry about that, I'm kidding and pulling your legs. But anyway, for the joy of the Americans, the red thing is the US cultural empire. Now, when I presented that many times in the US, you know, someone came to me and said, but how do you know that US is losing privilege of being the most important country in the world around the year 2050? Well, my answer was, well, you know, China is getting power. And so perhaps by 2050, China will be the most important country in the world, culturally speaking, in all sense. But nevertheless, we don't know about that. So this of course, is arbitrary. Next, please. Darwinian. So we go back to the full evolution of life. Now, oh my goodness, this is the geometric locus. This is a mathematical way of talking, sorry about that, of the bilognormal peaks. Next, please. So we have an exponential curve. The easiest way to write an exponential is to have two constants. Capital A is a multiplicative constant, and B, capital B, is a multiplicative constant for the time at the exponent. Well, if you assume that life on Earth started 3.5 billion years ago or so, which is what I have assumed, and in my opinion, that time, 3.5 billion years ago, refers to the appearance of RNA, the first molecule capable of reproducing itself before DNA. So anyway, if you assume that that occurred 3.5 billion years ago or so, then these two constants, capital A and capital B, come up to have these values. Capital A is 50 million species, that is 5 times 10 to the 7 species, and capital B is this thing. And this is over seconds. Okay, next, please. Now, here is something that I would like you to understand qualitatively. So I'm not giving you any equation now. Just look at the figure. We told you that this exponential is essentially the increasing exponential trend of evolution. Actually, in my book, practically speaking, this means the number of living species on Earth, the average number, not the exact number, of course. And consider these curves. The blue one that has the peak over the exponential, the green one that has the peak over the exponential, and the violet one that has the peak over the exponential. Now, what my mathematics did was to find out 3 different curves, all of them B-log normals. So this is the number 1 B-log normal, this is the number 2 B-log normals, this is the number 3 B-log normals, such that the area under each of them is the same, and conventionally that is assumed to be 1, which in probability is called the normalization condition of a probability distribution. So these are 3 probability distributions normalized to 1s. But the point that I would like you to notice, please, is that as long as the time elapses, the peak is higher and the width here at mid-peak is narrower. What does that mean? Well, it means that as long as civilization progress, they become more and more evolved, which is what we notice, but also at the same time, they last on the average less and less, which means that, for instance, for the empires of history that I mentioned earlier, the Greek Empire, the Roman Empire, and Italian Renaissance, and so that is in terms of centuries, but after the final point, that will be in terms of much smaller time units. And I tell you what, this is my opinion, the advent of artificial intelligence, which is what the scientists call the singularity. And actually, there could be much more to say about that, but I don't want to say that now. Heath, please, next. Now, geometric Brownian motion, GBM. Next, please. Now, these are 2 different realizations of the geometric Brownian motion. The blue one, the upper one, and the green one. They have different values of the 2 independent parameters. For instance, for the blue one, mu equals 1 and sigma equals 0.2. For the green thing, you have mu equals 0.5 and sigma equals 0.5. But what you can immediately see is that the mean value is increasing exponentially. Okay? Yes, Dave? Okay. Next, please. Now, I will send you the equation, but essentially the mean value, these 2 round brackets means mean value with respect to time, of course, but also with respect to average, which means that the process is ergodic. Anyway, the mean value of the stochastic process, capital N of T, that is the mean value of the number of living species in time on Earth, is a constant, n sub naught, times 2e raised to the mu constant t. This is the equation, but I'm not going to tell you more about that. Next, please. Darwinian growth is a GBM in the number of living species. Next, please. Let me please give you just 4 papers that with your time, I would honestly suggest you please to read and ponder over. First of all, this paper was written by me, of course, in 2014 and published in the journal called Acta Astronautica. Acta Astronautica, just because I am a member of the International Academy of Astronautics. And the title is self-explaining, SETI as a part of big history. This is the first such paper that I would like to suggest. Next, please. The next one was published by me in the International Journal of Astrobiology, and the title is SETI, Evolution, meaning, of course, evolution of life, and human history, which is what big history usually refers to, merged into a mathematical model. Okay, next, please. EvoSETI, a mathematical tool for cladistics, evolution, and SETI. What is cladistics? Well, cladistics is the science of the tree, logical tree of evolution over time. So, of course, we start with DNA, RNA, and then DNA, and then look least common ancestor, and so on, and then you keep going in time. But cladistics is the art of arranging that in a logical sequence. So you don't make the mistake of putting new species before older species. Okay, thank you. Next, please. And finally, this is very, very, very recent. It was just published a few weeks ago, 2 weeks ago, in the International Journal of Astrobiology. The year is 2023. The pages is 110. And this again is a mathematical paper by Eugenio Mieli, who is a co-worker of mine, Andrea Valli, another co-worker, and myself. Astrobiology, that is hopefully much of astrobiology, resolution of the statistical Drake equation by Maccone's log normal method in 50 steps. Again, this is a long and mathematically heavy paper. Sorry. Next, please. Now, good news. Why good news? Because so far I have only been talking about B log normals. That is, log normal curves that start at time B and then reach the peak and then finally go down. But in my analysis and in my book, I discovered two more curves that I would like to present very, very concisely to you. The first one shown here is called the log par. That means log normal and parabola, meaning that this is the curve. And again, I am using the Rome example just to give an example. So the civilization starts in 753 and so on, reaches the peak at the time of Nero, and then it goes down immediately as a parabola. So this branch here from the peak down to 476, the collapse of the Western Roman Empire, is an arch of parabola. And the history equations for the log par are not the same history equation as for the B log normals. These are the history equation for the log par. They are not very different, but they are different. For instance, there is a factor of square root of 2, which is 1.4, whatever. But they are different. And so this is the log par. And in my book, there are many examples of log par curves. And after that, next, please, I would also like to mention the logel. What the logel is? The logel, as the name says, is log normal and ellipse, meaning that the red part is log normal again, just as for the log part. But the blue part here is a quarter of an ellipse. And here are the history formulae for the logel, which are slightly different from the previous history formula. So it's up to you, ladies and gentlemen, the big historian, to decide which one applies better to the problem that you are willing to analyze, okay? Now, let me please point out one thing, that these two curves that I mentioned, the log par in the previous slides and the logel now, have also a fundamental difference with respect to the log normals. You can discover the history equation only if you apply a principle that I call the minimum energy principle. What is the minimum energy principle? Well, in loose words, it means that every living species living with these things uses the energy of her life in a minimal sense, meaning that it lives and it uses the energy, but only the minimal available energy. Now, this is very important in my opinion, because it's what is the evostatic corresponding things to what in physics is called the principle of least action. Now, in physics, you can, in all physics, particle physics, and so on and so forth, you can show that the action of a system is minimum, always minimum. And here, this is the minimum energy principle of my Evo-Seti theory. Next, please. Oh, at last, Shannon's information entropy. Now, I claim that the Shannon's information entropy is the correct measure of evolution of life. Next, please. Okay, let me say just a few words. Of course, we are all familiar from elementary physics with the notion of entropy, but that entropy is usually the classical entropy of Boltzmann, Maxwell, Clausius, and the other physicists that in the 1800s discovered the theory of gases, which is excellent. It's a great step ahead in the history of science. However, that theory applies rigorously only to gases. But let me say with joy that we are not a gas. We are something more complicated than that. And so in writing my book, I came to the need to describe an entropy that is not the classical entropy of the theory of gases. It is the Shannon entropy of information theory that was published by the American engineer and mathematician Claude Shannon in 1948. What is that? Well, first of all, it applies to any probability distribution. So if f sub capital X means the random variable, x, small x is the dummy variable under the integral, and you multiply the probability density times the logarithm to base 2 of the same thing. So density times log to base 2 of the same thing. That thing becomes an integrand, that is a function to be integrated. And if you take the integral of the whole thing for the whole range of the independent variable small x, in general minus infinity, but in reality it could be much less, then with a minus sign in front, you get what is the definition of Shannon entropy. So Shannon defined this thing, and I have good news to tell you. If you want to compute the Shannon entropy of the B-log normals, you can compute this integral exactly, that is without any approximation like Taylor series or anything else, and you get this simple formula. 1 over the log of 2, this is just a normalization reason, times the natural log of square root of 2 pi. The square root of 2 pi, of course, comes from the Gaussian normal distribution, times sigma, plus mu plus 1/2. Next, please. Good. So we have defined a new entropy that I called Evo entropy, that is the entropy of evolution of life. And if you assume the GBM exponential, and if you compute the Evo entropy of the GBM exponential, you have an incredible surprise. I was honestly shocked when I discovered that, because I couldn't believe that that was as simple as that. The surprise is that this thing, ranging in between minus 3.5 billion years ago and now, 0 time, this curve, the Evo entropy, is just a straight line. Oh my, I expected a much more complicated curve. But that's not the case. It happens that this is just a straight line. And, after redoing the calculation a number of times, incidentally, the calculations are difficult. Let me just tell you that, let me confess that in order to do this calculation, I always needed a good symbolic manipulator. And what I did use is the NASA symbolic manipulator Maxima, MAXI, MA, that was developed in the time of the Apollo flight 50 years ago with NASA fundings and works wonderfully. You can download it for free from the web. Please do download it and enjoy doing some simple calculation like x plus x, and Maxima will tell you 2x, which is correct, of course. But Maxima does much more than that. I just mentioned my delight, the Euler-Lagrange equation. Euler probably in America is called Euler. In Germany it's called Euler because it was from Basel. But anyway, this code Maxima is what I use throughout the whole of my book. Now, good. Let's go back to the Evo entropy. And as I mentioned, this is just a straight line starting with the RNA at minus 3.5 billion years ago, and reaching a certain value now. What is the value? The value turns out to be 25.575 bits, because we are doing computation in information theory. Now, this is so, oh my goodness, sorry, I was going to say something impolite, but it's so easy that when I found that, I said, there must be some more hidden behind all this. I just stumbled into something that is very easy and not yet well understood. Well, here is my answer. I know that some people in the Big History Association don't agree about that. I do apologize. And actually, I am planning to publish more papers about that. But I won't tell you more about that until I have published papers, because this is just the principle for serious scientists. You have to publish first, and then you discuss. Anyway, in my opinion, this thing is the so-called molecular clock. Discovered by, I'm using the German pronunciation because it was Austrian, Emil Zuckerkandl, and the famous American Nobel laureate Linus Pauling as early as 1962. And what is the molecular clock saying in plain words? Well, it is such a great discovery because it means that if you consider two species, and to my students, I always made the example of horses and humans, two species, and they separated in the course of evolution about 30 million years ago, 40 million years ago, something like that. Now, each species, of course, has blood, and blood has a special molecule that doesn't come to my mind at this moment. Sorry about that. But anyway, this molecule, this is the cytochrome C cytochrome. And from that, you can reconstruct the DNA of both species, the DNA of horses and the DNA of humans. And then if you check the two DNA's molecules against each other, you will find that much of the two molecules are pretty much the same, but not completely, of course. There are differences. And the number of differences between the two DNA molecules is proportional, that is linear proportionality, to the time that has elapsed since the two species diverged in the course of evolution. So this is in plain words, of course, but you can find more in the literature, the molecular clock. And my claim, I'm sorry, I'm not being modest, and I do apologize about that, but my claim is that my evocity theory predicts that this must be the case because the evo entropy of the GBM exponential is precisely the linear, the straight line given in this plot. Next, please. Same story. Time in between minus 3.5 billion years ago, 0 is now, straight line, evo entropy of the latest species in bits per individual. You also have to take into account the number of individuals, but I'm not going to say more about that. And this prompts you a unit, which I call capital E, EE, meaning Earth evolution or Earth evoentropy, and this is 25.5 bits. Next, please. Now, civilization differences. This is the trick. If you go through all the calculation, you find that the entropy, Shannon entropy, of course, difference among any two civilizations having their two peaks abscisse, that is the two times, at p sub 1 and p sub 2, this difference is given by this thing. Now, this is again a straight line in the difference, of course. So entropy is a measure of the level of progress reached by the second civilization with respect to the first civilization. And the entropy difference measures the difference in civilization level among any couple of civilizations. So if it is known when the two civilizations reach their two peaks, the above formula yields the civilization level difference. Next, please. Okay, so you may wonder, what is the difference in evolution in between nowadays humans and RNA 3.5 billion years ago? Well, it is precisely the number that I mentioned, 25 point. Pardon me?
Claudio, can you hear me?
Yes, I can.
Yeah, maybe we could take a little bit of a break and clarify some things earlier.
Sure. Well, I don't have many. Sorry, I don't have many slides. May complete just a few, 2 or 3 slides, and then it's over, and we have all the time. Thank you. Next, please. Next, please. Okay, so these are the example, and it's nearly the conclusion. Of course, I'm thinking about SETI, the difference in civilization when we meet the first extraterrestrial civilization. We have not the least ideas about that at the moment, but now we have a mathematical theory that allows to estimate this difference in civilization on the basis of the message that possibly extraterrestrial will send us. Next, please. And this is the conclusion. We have developed a new mathematical theory, you know about that. It is based on the properties of the log-normal probability distribution, and it should allow us to find the difference between us and an alien civilization when we discover the first civilization. Next, please. And next, please. Thank you very much indeed for your attention. Thank you. I have finished.
Thank you very much, Claudio. Okay. Can you hear me, Claudio?
Yes, I can.
Yeah, we can't hear him. I don't know. Turn my...
David, I hear both of you. Do we want to open the floor up for questions? Claudio, do you see the Q&A button on the right-hand side of your page?
Just a moment, please. Oh, goodness.
There's a chat button, and just underneath that is a Q&A button.
Chat button. Oh my goodness! On the right-hand side. No, sorry, I don't see it. Sorry.
Okay, that's fine. So I'll read a question from Gustavo Lau.
Yes.
One criticism one criticism to geometric Brownian motion in finance is that it assumes that volatility is constant. What leads you to assume that in evolution, volatility does not change over time?
Thank you for asking for that. Well, look, honestly, the answer is I don't know. I just took up the geometric Brownian motion as it was used in financial mathematics, and I try to fit it at best to my theory. Certainly, you are right. It should need more refinement. But, it took me already 10 years to write the City book, and I am also age 75. So I really don't know what to answer your question. Please accept my apologies, but I'm being very honest, and this is the truth. Thank you.
Okay, can you hear me?
Yes.
Yes, I can hear you.
Very good. You can hear me without the loud feedback.
Yeah. Well, no, not now. You guys need to turn off any microphone in that room except for the one you want to talk through. That's what's causing the feedback. So if Lowell has his on or whatever,
tried a lot of different combinations.
Yeah.
So Heath, can you go to slide 14?
Yes. Give me just a moment.
Slide 14, please.
Yeah, I'm working on it. Hang on.
Now we can't hear a thing that they're saying, I don't think.
I hear you, David.
Okay, good. I think we got it now. Can you go to slide 14?
Mm-hmm.
Is that what this is?
That is slide 14.
I think yeah. Okay. Go. We want the one with the Roman and the Greek Empire. There you go.
Yes.
That one.
Okay.
Sorry.
Got it. Thank you.
Okay. So we were wondering, where would the Alexandrian Empire be?
Alexander the Great, you mean?
Alexander the Great, yeah.
Yes, thank you. Well, I didn't give a specific bill of normal for that. I just gave the bill of normal for the whole Greek civilization, and this is the red curve. So Greece.
So can you estimate it?
Well, yes. For instance, it ends at 30 B. Please remember that here you have to keep in mind that this is a tangent line going to touch the time axis at the time 30 before Christ. And this is the time when Cleopatra committed suicide. And so Egypt became a Roman province, okay? So Alexander the Great, of course, comes before that. And roughly speaking, is around here in between the peak, which was, in my opinion, the democracy in the time of Pericles, and of course the Hellenistic world. So the Alexander the Great peak is, of course, it could be the peak of an empire. The bill of normal would be slightly different. But my guess
if you normalize that like you did all the others, how high would that be?
The Greek civilization was normalized, as I mentioned.
Yeah, we speak about Macedonian civilization. Macedonian civilization was quite separate from Greek. Yes, and the Greeks did not consider Macedonians Greeks.
Oh, sure. I should. You are right, but that would mean to give a much more detailed picture about this part of big history, which can be done, of course. I just didn't do it.
But yeah. What would it look like?
It would look like a few different bill of normals, each of which is enveloped by an exponential, at least for the time considered. So you can do that. It's easy. I gave you the equation. You just change the inputs B and D, and so you can draw it. I mean, there is nothing special about that.
And if you draw it, I think the height of the peak would be much, much above that black line, right? Because the area underneath has to be constant, right? So if you make it much shorter, the height of that decreases, right? So the US in red at the end is super high just because it's a very small time frame. Rome is lower than the Greece because it was a little bit longer.
Yes, yes. No, you are right. You are right. Let me give you good news for your point of view.
Okay.
These are all Bilog normals. But if instead of Bilog normals you use the log pars, you remember the log pars, the log normals plus parabolas, then you get exactly what you are expecting. That is, the Greek peak is much higher than the Roman peak, and so on.
I mean, you could use triangles to approximate these as long as the area has to be constant.
Yes,
The short,
and I did it. If you please look in my book, there is a part of the book that deals with log pars. And again, in terms of log pars, this diagram does not work anymore. It's completely different. The Greek log par is much higher than the Roman log par, which I'm glad, because the Greeks were much more civilized than the Romans, in my opinion. And so on for the Alexander Empire, and so on and so forth. So please do that with the log pars and not with the Bilog normals.
It doesn't matter what function you have.
No, but there is a difference.
But if
because
it is measure of civilization, it's
normalized.
It loses any sense.
So can you go to the one where you do the lifetime and then you find the entropy from that based on Shannon's formula?
This one?
No.
It's a long equation with the integrals.
A
little bit further on.
Further.
Okay.
Just keep on going. And a little bit further.
A little bit further with integrals.
So my question is, why should the entropy?
No, earlier.
No, this is the log
a little bit earlier than this.
Earlier, there should
No,
be
no, it's later than that.
Integral signs.
It's
Yeah, there
later
you go.
than that.
Yes,
Yes.
Okay,
that's it.
so there's a couple things with this.
Yes.
One is, why do you think that the entropy of a civilization is just based on its life curve?
Because here we didn't talk about the energy in the game, but the energy plays a real important thing.
Yeah,
Okay.
You don't have energy in there. You just have how long that civilization lasts.
Yes, but if you regard the log pars and the logels as power measured in watts, power curves, then the area under that curve is, of course, the whole energy that has been used by the civilization during the whole lifetime of the civilization itself.
So that's assuming that the energy of Roman civilization is the same as, for example, the U.S. civilization. And I think you know that that's not correct.
Of course not. But that was assumed in Bilog normals, not in log pars. If you use the log pars, then you can divide the two energies and to see which one it is. Unfortunately, I didn't put here the images of the log pars.
Yes,
but in my books they are so.
Yes, technical question important. There is another paper, the second paper on this panel. Do we have time for the second paper?
I've got a hand raised by Alberto. Can we get to Alberto's question real quick?
Okay, one more thing on this is that it's a conceptual thing, but also a mathematical thing. Is that the Shannon entropy equation for discrete distribution does not go into this type of integral form, continuous. There's quite a bit written on that.
Of course, it's a summation rather than an integral. We know about that.
So this is not the Shannon entropy.
Well, I don't know. Maybe it has different names, but anyway, this is the formula that I use throughout my book for the continuous thing. I didn't consider discrete things.
Okay. Heath, you want to get the person with the hand raised?
Yeah, let me get
Thank you.
Alberto. I have you on the stage.
Yes, I'm here. Can you listen me?
Yes, I can hear you.
Okay, thank you. Thank you, Claudio. I think that the focus of your work is that you use very sophisticated mathematical models in order to compare some civilization of our human history. Maybe some other civilization can be modelized, maybe Muslim, Chinese. But the question, the reason why to make this comparison is to be aware in the case of a meeting of our human world civilization with some extraterrestrial civilization. I think this is the focus of your work. You have some instrument to compare ourselves with other civilization. Can you give make some more words about this question?
Yes, thank you, Alberto. Well, let me tell you that, of course, I work in SETI, and of course, we did not discover any other civilization. However, my suggestion for future research by anyone is that rather than looking at the whole civilization as I did in my book, just look at the tiny part in time that is stellar evolution in between the origin of the star and the star as it looks now. If you do so, then you can compare the evolution also of molecules, interstellar molecules, that we expect to find in the atmosphere of these stars. And then you can find out what is the tentative distribution of prebiotic molecules in the space around the Earth and in this galaxy, okay? So the point is that rather than giving the whole story from minus infinity to plus infinity in time, you should just confine yourself to the time between the birth of a certain star. For instance, for the sun, it was, the birth of Earth was 4.5 billion years ago. The birth of the sun was something like 10 or 12 or what, 10 billion years ago. And the situation of that star nowadays. If you do so, then you can compare the results. Thank you. Okay.
All right, Heath, do you see any other questions in there?
Let's see here. So one other question from Gustavo. Another criticism of geometric Brownian motion in finance is that it assumes stock price paths are continuous. What leads you to assume that in evolution, there are no jumps caused by unpredictable events?
I'm sorry, you know much more than I about financial application of geometric Brownian motion. I don't know how to answer this question. I should do much more research in this, but I am not an economist. And I have to say that I have been trying, of course, to derive all the equations that Black and Scholes and Merton discovered and that gave them the Nobel Prize. But this is not an easy thing at all for people not familiar with financial mathematics. And of course, you are familiar with that. I just derived some of them by virtue of this Maxima symbolic manipulator that I got from NASA. And it was a difficult thing, I have to say. So probably there should be more books written in the future. You could write one if you want, criticizing my theory with regard to the Black-Scholes models and pointing out your questions. I am just not able. Sorry about that.
Excuse me, but there is also very relevant questions of Mark Chitola. What are the units for the y-axis on these two envelope slide? Because I also.
Yeah, okay. Did you hear that, Claudio, from Mark Chitola? What are the units for the y-axis on this two envelope slide?
Yes, yeah. Excellent question. Thank you. Okay, the units for the y-axis depend on whether you assume B log normals or log pars or log-Ls. So if you assume B log normals, that is normalized curves, of course, the area under the B log normal is always equal to 1 by definition. But if you assume log pars and log-Ls, the area under the curve is the energy that species has been using during the life. So for that case, the units on the vertical axis is joules energy. Oh no, I'm sorry, watts. Energy is the area under the integral, the area under the curve. Watts. These are power curves in watts for both the log par and the log-L case. Thank you.
Is that per person or for the whole civilization?
Like 0.034, which seems to be something. This should be terawatts or something like that.
Could be. Could be.
But so it's not clear what I think.
But I don't know. We have to measure things carefully.
But, even for with terawatts, United States consumed perhaps much more than many terawatts per year. Yes.
Look, I told you what I could do and what I could describe to you. No more than that. Please accept my apologies, but that's my legacy to future generations. And I'm sure that this conference was useful because people came to realize that you can hope for putting mathematics into this kind of big history things. Thank you.
Very good, Claudio. Well, thank you very much for your talk and answering these questions. That's excellent.
Thank you, Dave, and thank you all the people that have been attending this meeting. Thank you and good luck.
Very good. Thank you.